go to the notes, shall we? Yay, the ratio test, one of the best tests, actually my second, third favorite test of all tests.
What's your favorite test?
The limit comparison, actually the divergence theorem is the best because it's the least amount of work. But then the limit comparison test is the best because it's cool. And the ratio test is second best. All right, here we go. The idea goes like this. You've got a series, and assume that we check divergence theorem, that the terms go to zero, so it has a chance. Or it's possible that there will be times when you're not sure if the terms go to zero, in which case you just say, all right, I'll just run another test and it'll answer my question. So if you check the divergence theorem, and if you're not sure, then just proceed on with the test. The ratio test works something like this, and then I'll talk about when you use it. But the idea is to see if the terms get small quickly enough. The divergence theorem says the terms have to get small. Then you go better and say, all right, it has a chance of converging, but do the terms get small fast enough? We talked about in P-series, there's a very fine line between getting small fast enough and not. This gets small fast enough, and there is a finite sum to this, but that small change of an exponent crosses the line into divergence. Yeah, these terms get smaller, but you never reach a top floor on the sum. It just gets bigger and bigger and bigger and bigger. And so it's not enough to say the terms get small. They have to get small fairly fast. Now, what does fairly fast mean? That's where the test comes in. There's a numerical test for fast enough. The ratio test goes like this. You compare a later term, given the formula for how terms are generated, you compare a later term to the one before it, the n plus 1 term to the one before it, the nth term. And you say, what about that ratio? Well, if that ratio is less than 1, that implies that a later term is less than an earlier term, and it will converge. If a later term is greater than 1, well, that would mean diverging. And actually, I got to be honest with you, if you check the divergence theorem, that usually, you never even see that case. That would happen when you weren't sure if it passed divergence theorem, all right? So if a later term is greater, this ratio comes out greater than 1, diverges. The bummer is when the ratio comes out to equal 1, which might happen in the harmonic series. Then it's an inconclusive test. It doesn't really tell you how they grow in comparison to each other or much, and so you have to use some other tests. All right? So this, when do you use this? Actually, I'll come back to this in a second here. When do you use this? Well, if you have a problem with either exponents or factorials, or a mixture of both, then the ratio test works really, really nicely. Let me give you an idea of what this looks like. Is this, did I change this? No. This is what you have. All right, cool. So you've got a series here, and you want to see if it converges or diverges. We have talked about which of those is more powerful, exponent or factorial. Factorial. So it has a chance to converge because the terms do go to 0. The factorial outpaces the exponential. Remember, that just means it might converge. We can go on. We hoped for the best case. If the terms don't even get smaller, we're done. But it has a chance, so we need to go on, right? The ratio test goes something like this. You compare the n plus 1th term to the nth term as we go down, down, down the line. As we go down the list of terms, how do the terms compare? Now, the n plus 1th term, the top is 7 over n plus 1. Because we're talking about the n plus 1th term, we replace n with n plus 1. And n factorial is n plus 1 factorial at an n of n plus 1. You with me? The denominator, a sub n, is the term as you see it, so you just copy that down. And now we need to do some cleanup. You'll get better and better at if you're not already good at this, but this is a huge skill for series work. You need to be able to manipulate algebraic terms here, and you typically do it by breaking it up into pieces that will cancel. So 7 to the n plus 1, you're going to call 7 to the n times 7 to the 1. Exponent rules in reverse. N plus 1 factorial, you're going to call n plus 1 times all the things beneath it. Well, what's all the things beneath n plus 1? N factorial, right? Now the thought being, you want to take the larger one. You might write yourself a note. Take the larger term down to the level of the smaller term. To cancel. Now rather than leave that denominator down here, I'm going to take it up next to and reciprocal, all right? So when I take this guy up, it becomes n factorial over 7 to the n. You see where I'm coming from. Dividing by a fraction is times the reciprocal of the denominator. All right? With a little... As n goes to infinity, what is 7 over n plus 1 approach? 0. Okay? Now is where we show the theorem has been satisfied. The theorem is, there's actually 3 parts to the theorem. If the limit is less than 1, we conclude convergence. If the limit is greater than 1, we conclude divergence. And inconclusive is worthless. In this case, we found the limit to be less than 1, so the series converges. We satisfied the condition of the theorem. The limit is less than 1, therefore we can use the theorem to conclude it must converge. You see what I'm talking about? Okay, try the next one on your own, please. Now, what that means really, what you just found is because that limit went to 0, that means the factorial went big much faster than the exponential. That's really what the nature of that 0 means.
Really doing the divergence theorem, that's a 0.
Yeah, so that's a good question. What about that? Does it pass divergence theorem? If you're not sure if it passes divergence theorem, then just go ahead and run the test. You can, if you're not sure if the terms get smaller, the test will tell you later. You run the divergence theorem first because when it fails, then that's the least amount of work. So that's the best case. That one's a little tricky. You have to think your way through that one. How's it going? If you're not where I am, try and get where I am because that's the way you should be approaching it. Why? You didn't have a question? I
No,
thought
I
somebody
do have
said.
a question.
Oh, yes, hit me.
Why? Okay. So for the B to C,
Uh-huh.
for the e to the n plus one squared, why could you not just do like e to the n plus one times e to the n plus one?
You could.
Could you?
You could. Yeah, that would work.
Okay.
Yeah, you would end up in the same place as I would.
You would?
Yeah, so if you did that, it's totally logical. I understand what you're saying.
Okay.
Oops. It wouldn't be, actually, I take it back.
I feel like.
It would be this. If it's squared, it would be that times that.
Oh.
Yeah. So I take it back, that wouldn't work. Okay? All right, so when I get in step D, I tried to break it up so that I could get some like terms. Okay? That leaves me with n plus 1 over e to the 2n. The e is nice, but it doesn't do much. So which wins, the n plus 1 or the e to the 2n? E to the 2n. And so this limit goes to 0, which is less than 1, and therefore this series diverges. Converges. Sorry. Converges. All right. Are you with me? Okay, let's go on to. There's nothing more on those notes, is there? Okay, go to the back side, please. The root test. The root test is one of those things where it's a tool where it's not useful in a lot of situations, but when you need it, you really need it. So there's no other way to go about it. So it's worthwhile to have. But in terms of usefulness, the ratio test is far more useful than this guy in more cases. All right. So say you are dealing with a geometric series. Basic common ratio to an n. Yay? All right. Some things we know about geometric series is that if this is geometric, r should be a constant. It should be, 1/2 to the n, not n to the n, or n plus 1 to the n. All right. To be truly geometric, that should be a constant to the n. The series converges if r is less than 1 and diverges if r is greater than or equal to 1. All right. Now, that's the starting point for the root test. The root test also deals with an n as an exponent, but it deals with cases where the base isn't constant. Where, for example, you have a case like this where instead of 2 to the n or 1/2 to the n, it's some varying thing to the n. Well, then you can run what's called the root test on that using 1 pretty much as a guide. The idea is this. If you take the nth root of that, so you're basically just looking at the interior, the base. If you take the nth root of that formula, and that is less than 1, then it's like the geometric case where the base is less than 1 and it converges. Okay, so if the nth root of the term is less than 1, converges. If the nth root is greater than 1, it diverges. Now here's the only slightly different thing than geometric. When the test equals 1, that's a bit of a gray area there, and the test is not diverging like we would think geometric would be. It's actually inconclusive. 1 is its own special case, and so you'd have to go back and use some other test. It's a measure of whether things get small fast enough. Let me show you how this might look. If I looked at this, I would say, oh, there's a to the n. It's geometric, but no, the base is not constant, so it's not geometric. I would still do the divergence theorem. Do the terms go to 0? What is the limit of the term? What is the inside approach? 2/3. And 2/3 to huge powers would go to 2/3. What's 2/3? What's 2/3 of 2/3 of 2/3 of 2/3 of 2/3 of 2/3? The terms go to 0. Taking part of a part of a part of a part of a part goes to nothing. So it has a chance. It might converge. Now, because of this, I didn't put the indices there. I got lazy, sorry. But because of the exponent in there, I'm going to try the root test. The idea is you take, as n goes to infinity, the nth root of the term formula. Now the nth root of 2 to the n is just the inside. In other words, now we're going to just focus on the base. What does the limit of the base approach? 2/3. Now, the test would then say, because that test came out less than 1, we conclude the series converges. We satisfied the first condition of the ratio test, the first test. If it comes out less than 1, we conclude convergence by the ratio test, or the root test, excuse me. You do not have to say by the root test here, the person reading it understands you're using the root test. But if you want to throw it in there because you're that kind of overachiever, good job. Okay? Try the next one, please. Yep.
Is it like a few series have like there's like convergence and divergence, like that's it?
You don't find the sum. Is that what you mean? Yeah, we don't. This is again one of those where we don't find a sum for it. We would probably use a, a manageable. Actually, I'm so glad you. So, can I just little? You just reminded me of something. Okay, if you're not sure if this converges or not, and you're using your calculator, please by all means do a series from 1 to 100,000 and see what happens. But if you're using my calculator, please don't put that into my calculator because this is still calculating a series from the test last week that somebody did. It's just locked up into a series that's rounding around because somebody said, give me the sum from 1 to 100,000.
Guys, who did that?
Dude, come on.
Miss Canton.
I'm going to have to reset.
Someone did that last year. They took it up to her and she was like, that was so stupid. I can't do that. I was like, loser. I was like, I didn't do that.
Was it you?
No, it wasn't me. Hey, actually, you need to take that back.
Please, I mean, it's not a terrible thing, but I guess if I were you, you have no other choice, and you're trying to see if it converges, then build up to it, try 20, then try 30, and try 100 maybe. But geez, going straight 100,000, you're going to lock up your calculator, and then you're going to panic on the AP test, and you'll be crying, and I will cry too, and then we'll all be sad. All right? Try this one. Go. Yes.
Why do you have to do this whole little thing? Can't you just like warm the inside and be like,
That is what the root test is.
but like,
How does that work?
I just don't understand.
Why does
Good
it
question. We'll get, not everything is quite so pretty.
Calculus makes you all these stupid steps.
Did-
Like, just jump the gun.
Okay, so you say this fails the divergence theorem.
I feel like it's gonna diverge.
What do the terms go to?
3 halves.
3 halves.
Oh, I just cracked.
No, wait.
Actually, it goes to 3 halves to the end, so that goes to infinity. And so this diverges.
See, got a big pot of-
Now you might see
That was my best.
that diverging root test often is caught by the divergence theorem, but not always.
Are one of these in dates which is fuzz number?
Okay? Would you let's go look at the next one, shall we?
Oh, I think you can get me on this one.
Okay? So, look at this.
No, because it's a little missing.
I might start by playing around with this one a little. This one's a hard one, isn't it? Guys,
But
look,
even
which
then
is
it
good.
plus 1 over e.
The mind's calculated.
Goes to your-
Why does this work, Mr. Aikman?
Yeah.
Good question. When we look at the numerical cases below, it might help.
Okay. Feels like I'm just doing
Because
this.
it's 1 over e a
Yeah.
bunch of times. Wait, but it's 1 over e to the negative n, so when is it e?
I say remove.
Wait, what?
It's gonna be e to the negative.
I don't know
One
about
over
you.
e to the infinity, so it's gonna go to 0. So therefore,
But why is it not 1 over e?
because when you bring it, because it's the negative n, that here, when you bring it into that denominator.
But why is it not 1 over e to the first?
So that's what it's equivalent to, yeah?
Yeah.
Which is 1 over e.
1 over e to the nth.
Might it converge?
No, it's 1 over e to the first.
Yes, it might converge. Okay, so now let's try the root test. If we try the root test, the limit as n goes to infinity of the nth root. Yes.
Your rationale for the last one that we did was infinity doesn't equal 0.
Right.
So then
1 over e doesn't equal 0
1
either.
over
Yeah,
e
do you
doesn't
want to
equal
explain
0.
that?
Oh, good point. My bad. Darn it, I was trying to come up with an inconclusive. Shoot. All right. Well, this is supposed to be inconclusive. You're right. It's not 0, so it diverges. Darn it. I even tried. It's hard to come up with an inconclusive test. I'll find it. All right. Look at the last one, please. This is the one that tends to kook students out. All right. Now, because of the end there, it's not geometric.
So we do the n plus 1. That's going to be no.
No, that's really gross.
And it is not okay, like an integral problem, it's not okay to split a product into two series. This you shall not do. That's also a no-go. Okay? Now then, you need to figure out, does this converge or not? Does it even pass divergence theorem? Do the terms go to 0?
Yes.
Yes, it has a chance. All right? So we could try a couple different tests. We could try ratio test actually would work here, but let's say we tried the root test. If we took the root test on this, then we take the nth root of n to the 5 over n. Now the top, this is something that requires a little bit of instruction, but the bottom comes out to be 5. Pretty cool so far. Yes? All right. You'll see that top happen once in a while, especially with the root test, but in other times too. In Maclaurin series, this will start to happen. So you need to be familiar with that. So let's say we take a little side investigation. If you have, somebody has a calculator out, can you help me out here? The question is, as n gets huge, what happens to you when you take greater and greater roots of greater and greater numbers?
I don't know.
The square root of 2 is 1.4-ish. The cube root of 3. What is the cube root of 3? Something times itself that equals 3. So it would have to be above 1. 3 to the 1 divided by 3. 1.44. 1.41. 1.44. 4 through to 4. What times itself 4 times would equal 4? Talk to me about what kind of number that would be.
It would also be 1 that's above 1.
Close to 1, but couldn't be too much above 1.
No, I can't.
1.104. 5 to the, or 10 to the 10th is what I jumped to. 10 to the 1/10. It can't be very big because if you're taking it to the 10th power, it would get, oops, this one's not right. This is to the 1/14th power, sorry. Sorry, I typed
I
that
just
in.
don't understand why we use
Delete. 1.41. This is coming back down. This is 1.25. If you look at 100th root of 100, 1, it has to be, if you're asking what times itself 100 times equals 100, it can't be very big. It would have to be just above 1, yeah? So as n goes to infinity, this approach is what? 1. Excuse me, because that limit is less than 1, the test or the series must converge. Would you write yourself a note here? The ratio test also would have worked. I think if the limit came out to be a 1/5, also works. Yeah. And it's one of those things where the ratio test works in some cases, more cases than the root test, but cases like this, you wouldn't do a ratio test, it would be a mess. So tomorrow we'll do extra practice on it, and it'll start to look a little cleaner, and we'll make sense.
The root test, correct?
Right. Can I call it the ratio?
Ratio.
Oh, shoot. My notes are mislabeled. That box is called the root test. Shucks. sorry. Alright, should we do one or two off the homework? Since we don't have homework today, might as well crank out a few off the homework. Let's,
You should propose a t-shirt.
I should?
Would you like to write on this opinion?
I told Miss
Yeah.
that we would give her
Let me
So you need to
do
send
a
an
homework
email
and
with
two
pages.
I've never done t-shirts before. Is that the process?
What's her shirt?
How do you do it?
Well, we just say, you just say, do you guys want to do a t-shirt? If you guys have any dope designs, you can go ahead and you can vote on those.
Oh. And then what happens? Then I have to order t-shirts and stuff? I
No,
don't
you
need
don't even,
that.
I can order the t-shirts. I
Really?
just gotta click one. And would you like one? Mr. McCullough's got ours.
Yeah, oh yeah, definitely. Let me see. Let's talk about it in a second. Here, so set 130. Would you try number 3? I should do the How are we doing? Okay, so here's the thought process I go through. Do the terms go to 0? Yes, so it has a chance. Go on then. Is it a known series, like a P series, a geometric, or a telescopic? It is not. Is it like a known series? I actually could split this into, but no, it's not like a geometric or a P series with the constant, so it's not a comparison test. That would be a comparison test if it was like a known series. Is it integrable? That's the word, yes. Integrable means able to be integrated, like differentiable. Integrable is a word. Okay, is it integrable? It is not. Factorial is not continuous. It is not integrable. Okay, I didn't make up a word. That's a word. It is a real word, integrable. Go ahead, please do. Okay, does it have exponents and or factorials? If it does, that's a possible candidate for the ratio test, and this is a candidate for the ratio test. Or does it have something to the end, but it's not geometric? That might be a root test. All right, so in this case, I lean towards ratio test. Did you learn to use the ratio test?
Yes.
Okay?
I did.
In the ratio test, does it look something like, did you have a finite sum plus 1 factorial over n plus 1 over n factorial? Something like that.
That's what mine said.
Okay, so as it goes to, so n plus 2, yeah, it's fine the way it is. I guess I could break it up into n plus 1, but I won't. N plus 1 factorial is n plus 1 times n factorial. If I take the reciprocal of the denominator, it becomes n factorial in the numerator over n plus 1, n factorial. What about n plus 2 over n plus 1 squared? It goes to 0, which is less than 1, and therefore converges. All of that is necessary. This is the test. If you fail to write less than 1, you failed the test. You did not complete the test. It is not enough to say, hey, the limit is 0. You know what the test is. You must say, the test is 0. It gets the test statistic, which is less than 1. It converges. Failure to write this will cause failure on your part. All right.
Really tough.
Other questions? Should we do another one? Okay. How about 4? Yay, 4 is a good one.
I feel like just picked the set ones.
They're all good ones.
That makes absence.
Try 4.
Can we do one root test?
You don't want to root the n factorial, so no. But where is the
That's not
root
what I
test problem?
No, that's not.
No. My question is, can we do a root
Why would
test?
you want to though?
It'd be good to get practice on the root test, and it would work on.
I don't think you're understanding.
This is infinity. Yes, yeah, I think so. Yeah, that's definitely divergent. Oh, it's n factorial. I thought it was just over n. Sydney, I made a poor mistake.
Okay, let's do 8 after this. Are you ready?
No.
No. ¿Listos?
No.
Yes.
Okay. So did you use what test did you use? The ratio test. And when you found your limit, what was your limit? 0. And so you concluded converging, eh? Okay, where'd you jump to 8? 8's fun. Okay, now, before today, how would you approach 8? Separate and use geometric, okay? That would work, but let's say we use the root test, all right?
Oh,
The limit as n goes to infinity of the nth root, 2 to the n plus 2 over 3 to the n. Now, think infinitely. When you get huge numbers, which 2 to the n would go to, does that plus 2 start to mean anything? No. So that 2 means less and less as n goes to infinity, and this limit approaches 2/3. 2/3 is less than 1, and therefore this converges. Okay? You with me?
Oh, yeah, that's
For huge numbers, a small constant being added is meaningless, so the nth root of 2 over 3 to the n becomes 2.
a question.
All right,
But
so in that case, it's a little quicker to do that. Question? Yes? Number which? You could split into geometry. That's true. Okay. 4?
If you take the limit of just like the terms, could you do that anyway?
You could take the limit of the terms and show it's 0, but that just proves it might, not that it does.
Oh, but it doesn't. It just
Factorial beats exponential. So the terms definitely go to 0.
because it's like 3 times 3 times 3 times 3 times.
What if it were like 3 factorial? Like,
If it were,
it were a number not n, would it not win?
n factorial would still win because it would.
No, if it wasn't, it was 3 factorial.
Oh, this? Oh, yeah, that would definitely.
Oh wait, actually, that's
Yeah,
a
that
good
would,
question.
that would.
If you were to do what,
Geometric split?
what is that? The ratio one? The ratio one?
The ratio test
For
here?
ones that you know diverges, what would it come out to? Like an infinity?
It depends on the case. In most
Would it
cases,
come out
infinity,
as
it's
the same
sometimes
answer?
inconclusive.
Okay. So would it be the same answer as if you just took the limit straight out? Or like,
It would give you the same convergence or divergence conclusion.
well,
It would,
like,
it wouldn't come out to the same number.
what is this series?
It converges. Ooh, this is on the other day's homework. You couldn't do it, but now you can. You could do the ratio test.
I was just
Huh?
really
Try the ratio test.
this room.
Yes.
Could you do a short idea on the board?
Oh, yes. Okay. So, I don't know if anybody's interested in shirts for this class. I've never done shirts before, so this is all news to me. The problem is that this would definitely be BC only, that idea, because AB people.
Well,
Exactly.
you know,
Like,
you know.
We don't associate with AB, is that what you're saying?
So if you have
We don't
ideas,
associate with AB.
should we collect all ideas and then later decide? Okay, if you have any ideas for a AP calculus shirt, either throw them to me or throw them to Jordan, who's taking this on,
Oh, yes.
and we'll see if any of them.
Or look at this really cool one. You put it up there. Do you
Oh
remember
yeah,
this?
do you have it?
No, but I can write it.
Oh,
This
this guy had a really cool idea. I thought this is,
No, I think that one's on top.
No, that one's on bottom because it's
yeah. Was it?
No, wait, I think it's times.
no, it was like a function of it.
Function of it?
Yeah. Here, this is what it was.
Listen, I don't know. Okay, I just.
See, I thought it was that.
I mean,
Talking about
That's what you put
Well, we're just learning to see it, but
because it's we're just going so fast.
I don't want to get a shirt that says valor.
we're just so to that
No, here,
Miss Rickman.
this is a function of it.
Yeah. I actually think you need to parentheses
Yeah,
around.
I love it.
I don't think you need to parentheses around the vowel.
This is a function of it. I love it.
I know it's pretty good.
I would buy that shirt myself. That's pretty awesome.
That's our shirt idea.
Love it. If you have other ideas,
We have other ideas, but it's not gonna be that.
what? Did you? I love it.
Yeah.
There's just like a lot of
Where is it? Oh.
It's like we're just like
it's very much
I don't want a shirt that says valor.
Okay,
I'm so smart.
you're so smart.
Incredible.
If I didn't get your extra practice, make sure I get it today if you were absent last Friday.
I have a question for Fred.
Oh, I have one.
She's the same size as
There's so much.
not enough time.
Oh, wait, that's too good.
Well,
That's
Still not enough.
I did not get 5. I tried to. Yeah.
So, about small area or a big area. So there's gotta be a place in here where the area is exactly the one. This is.
So just keep it one.
So this so that we integrated this so that you can get it and set it into one stop. So integrate this like
I think you remember.
Okay. Mine is a lot less.
it was point.
I I signed up.
Mine is
for
0.8. Alex got really
0.126.
What? Yeah.
I love that shit. It's really-
Maybe?
Okay, so,
Yes.
so no, everyone else did poorly. I got 2 B's on my last math test. Pretty good. It's pretty good.
You're on a hot streak. Oh, I forgot to put the plan up for this.
Going up. Wait, is that all it is? A test?
Start doing it right now.
Extra practice? Oh, heck no.
Yeah.
Oh yeah, you never
Is
put
it a fun sheet or a fun packet? You're really testing me.
In a good way. Yeah.
So I was getting a lot of responses. You see a lot of responses on that.
I don't know if I did. Maybe I should do a better job.
Because no one really was like, that's what I want.
That's crazy. That's why.
I don't think
That's
I want what they
partially why
would
I
have
never
down.
proposed a teacher because
Well, Alex, what
go
else
for
would
it.
you
Go
want?
for it.
If you say we're so much better than Alex.
I know. I get what it's going for. I just don't know if I'd want that.
Oh, I thought you were saying it to be.
No, I know. Yeah, I'm not saying. I know. Like, I tell you. I'm not saying that.
You're up.
Oh, wait, what was the question? Oh, I wrote down the wrong value. That's it. Okay.
That'll do it.
You guys have your.
Oh, I forgot to start the recording.
Actually, that's a 7. I have to do things, so I won't be here.